Today's content is about the shear stress, shear strain, but because the shear strain and the shear stress relate to the subscript of the tau. So before we do that, let's talk about some other topic in chapter 1, the stress component. So through this section, we can have detailed understanding what is the subscript of the sigma and tau means. So I think in the textbook is chapter 1, 1.4 is stress and zero loading condition and stress component. So, and of course, we assume everything in the 3D space. It's not just 1D tension compression. So a general structure, it can be any shape. So let's say this is a structure in 3D space, and I define the coordinate system. Let's say this is the left-right x, upward is y. So right-hand rule out of plane becomes the z direction. And we also assume that in general situation, this structure in 3D space also have force, external applied force, and this force can be in any direction in this 3D space. So let's assume that we have some general force applied, F1, F2, F3. And F4. Or up to F5. So of course, I drew everything in 2D space on 2D plane, but you just imagine that the structure is in 3D space and the force can be in any direction in this 3D space. And of course, the structure is in equilibrium. And as structure engineer, what we need to figure out is that, let's say, passing through a random point. Let's put a point Q here. We want to know what the state of stress at this point. So for this point, we already learned that stress in general by definition is force over area. And for the stress at a specific point, we can just mathematically, we can using the limit of the force to an area, that area when the area is approach 0, it becomes the stress at a point, right? And of course, for this plane, because we are talking about force of area of that plane, so it can be the x plane, the y plane, and z plane, which means the plane that facing the positive x direction, or facing the x direction, facing y direction, facing z direction. So let's do it one by one. Let's imagine that if we, since we want to figure out stress on at point Q, so what we can do is that we cut through that point using the x plane. So let's say this is structure. And x plane, of course, it means it's a plane that is facing positive x plane means it's a plane that's facing positive x direction. So let's say this is a positive x plane. Okay. Ah. It's getting worse and worse. Yes. Okay. So now let's say this plane is facing the positive x direction. So we can say this is the x plane, or you can say that the normal vector. The normal vector is in the positive x direction. This is normal vector of the plane, and it's in the x direction. So we can say this is the x plane. So we can figure out, let's say passing through point Q, we take a small area, of course. So this is a small area on this x plane. And on this small area, I use delta A. The area is delta A. And it has force in the x direction. On this small area, I use delta px. This is the force on this x plane. And of course, it has shear stress also on this plane, but in the y direction and z direction. And this force, I use delta v, since we normally use v as shear force. And this is on the x plane in the y direction. So superscript is the plane and subscript is the direction. And similarly, we have on this area delta A, we have the shear force in the z direction, x plane, delta V, x, and z. So for finding the stress component at this point, we just need to take a limit. And when this delta A approaches 0, then it converts to a point, and that becomes the stress at that point. So mathematically, we can write as sigma x, which is normal stress, is equal to delta px, the force applied on this small area, divided by the area, delta A, and we take the limit. When delta A approach 0, it converges to the point Q and becomes a normal stress at point Q on the x plane. Similarly, for the shear stress, let's say if the shear stress on the x plane in the y direction is the shear force on this small area, on the x plane in the y direction divided by the area. And similarly, we take the limit. When delta A approaches 0, it becomes shear stress on the x plane in the y direction. And we have similarly tau x z. So it's delta shear force on the x plane in the z direction divided by delta A, the area. And when this delta A get close to 0, it becomes shear stress, tau xz, shear stress on the x plane in z direction at this point. So as you can see here, the first subscript represent the plane. The second subscript represent the direction. So let's say on this plane, x plane, x plane. And for the shear stress, this one is pointing in the y direction based on the coordinate system. So it's the y direction, and this component point to the z direction. So this is what the subscript means for the stress component. And of course, in some textbooks they use sigma xx, some textbooks they use sigma x. It's the same thing, because normal stress is always, let's say normal stress for the if it's sigma x, it can only be x-axis. That it cannot be xy, sigma xy or anything, because if on the x plane in the y direction, it have to be shear stress. So some tests with put sigma xx, and similarly you can have sigma yy and sigma zz. So basically mean that this is the plane. The first x is a x plane, and the second x means it's in the x direction. And similarly, you have the y plane in y direction, z plane in z direction, since it's always either xx or yy or zz. So in some texts, they just use the 1x to simplify this subscript. But we should know that the first subscript for especially with shear stress, the first one is always the plane. Excuse. And the second subscript always the direction. Any questions so far? What is delta P? Delta P is a force applied on the small area. Since area, I use delta A. So on this delta A, it is corresponding to delta P. It's internal, yes, it's internal normal force. Yes, thank you. So why this one does not have subscript? Well, I can put this one, since it's the normal force, it's on when it's on the x plane, it can only be point to the x direction. It cannot point to the y direction or z direction. That's the definition of the normal force, right? So, okay, so you can put x here, same as you can write as sigma xx or sigma x. It's the same thing. But basically mean that x plane in x direction, x plane in y direction, and x plane in z direction. Why when delta A approach 0, the normal force equal the normal internal force equal to that force equal to stress. Why delta A approach 0 to the normal internal force equates to the force? This is a stress. Stress definition is force over area, force over area, force over area. When delta A approaches 0, it represents the stress at that point. In the previous section, we talked about, we didn't have this part. So it's basically we were calculating the average stress on that area. Make sense or not? Other thing we have learned before today's class is all about we have the force over the area, and if the stress is uniform distributed over the area, of course, it is a stress on that area. But if it's not uniform distributed, we talk about like shear stress in the first section. This one means the average shear stress over the area. But now let's say if you want to know the stress component at a point, mathematically what we can do that, we take a small area around the point. So let's say this point is Q. We take a small area around the point, and when this area approach 0, this becomes the stress at that point. So this is what it means. And of course, we have x plane, we also have the y plane. So let's say if we no need to apologize. All questions are good questions. So if any time you feel concerned about anything, you can just ask. So let's say the first one is we cut through P point using the x plane, right? Now, what if we cut through P point using y plane? So let's say we have, it's not perfect, but you know what I mean. So now let's say this is the y plane. And on this y plane, again, I still take a small area around point Q, the point that I want to know the stress. But so now this is an area delta A. And on this area, of course, we have the internal normal force on this small area. I use delta P. And of course, this is a y plane. And you can also say this is the y direction, but normally we it's not necessary, because if it's on the y plane, it has to be in the y direction. This is the definition of normal force, internal force, internal stress. And for the shear, it can be in two directions. So let's say we have this is on the y plane. On this area delta A, we have a shear force. Is superscript is the plane and is in the x direction, subscript is direction. And similarly, we have on this small area, we have shear force on the y plane and in the z direction. So for the stress component, we do the same thing. So sigma yy, or you can write as sigma y, doesn't matter. It becomes, take the limit, delta p internal force, y, on the y plane, over the area, and then when the area approach 0, it becomes a normal stress at point q. And for the shear stress, now it becomes the y plane in the x direction. So it's equal to shear force on the y plane in the x direction and over the area limit a approach 0. Same thing. Y plane z direction equal to the shear force on the y plane in the z direction over area. And when area approaches 0.
I have a quick question.
Yeah.
So when you're deciding like the x and the y plane, is that just like arbitrary or is there a way to like slice it?
This is based on our coordinate system I put here.
Okay.
Yeah,
Because
I
I
rotate put this let's say x, y, and z, right?
yeah.
So then let's say if this is x, this is y, then this is z. And then if I cut like this, then this becomes a y plane. Makes sense or not?
Got you.
And now for if I cut in this way, it becomes z plane.
I get you.
Yeah, so it's not like randomly cut in any direction. It depends on our coordinate system. How you define the coordinate system. Any other question? Okay. And of course, let's continue based on this coordinate system. We cut through the x plane, we cut through the y plane. Of course, you expect we can also cut through the z plane. To save some time, I can write you the on the z plane the 3 component. Of course, it becomes sigma zz. The normal stress on the z plane in the z direction, and shear stress on z plane in x direction, and shear stress on the z plane in the y direction. And as always, the first subscript is always the plane. First subscript of the stress component is all represent plane, which means the plane is facing which direction. And the second subscript is always the direction. So if direction of shear force is in the x, then direction of shear stress is x. If direction of shear force in the z, then the direction of shear stress is in z. So first subscript is plane, second subscript is direction. So this is what we need to know the subscript of the stress component before we start learning the chapter 2 about the shear stress, shear strain, because they always have a subscript with the top. And of course, now let's say if we have a cube, we take a cube around the point Q. Then I can put it this way. same coordinate system, let's say this is the x, y, z. Since, of course, we know that they are orthogonal, so we know that if we have the stress component on all the three planes, we can completely define the static stress at a point. So now, since this is x direction, so we know that this plane should be the x plane. And on this x plane, we already talked about, we have three component: normal stress, sigma x, shear stress, tau xy, tau xz. So let's put on this plane. Let's use different color. So on x plane, we have sigma x, or you can write as sigma xx. Shear stress, x plane in y direction. Shear stress, tau x z. And we want, let's put in the matrix. So we have three components. On x plane, we have sigma xx, tau xy, tau xz. Similarly, on the y plane, now this becomes a y plane. And on y plane, we still have three components: sigma yy, tau yx, tau yz. So let's use, so of course, this is a sigma yy. And this direction becomes the shear stress, tau y plane x direction, tau y plane z direction. So again, put it here. On the y plane, we have shear stress, sigma yy, y, z. More color. And now this is the plane that is facing z direction, so this is the z plane. And on the z plane, of course, we have the sigma zz. Shear stress on the z plane in x direction, tau zx. On the z plane in the y direction, tau zy. So on z plane, I put the three components here: tau zx, tau zy, sigma zz. Now, these 9 components can completely define static stress at a point. So when you go to check the more advanced structure textbook, we normally put this as a 3x3 matrix, and we call this as static stress matrix at a point. And if we know the static stress at a point, and then it means that since these three planes they are perpendicular to each other, it basically means that it completely defines static stress at the point. So for any plane that is inclined, we can calculate based on this state stress. And of course, you need to do the transformation, but basically we can just using this one, and for the inclined plane, what is the direction, cosine theta and everything, we can find whatever the inclined plane, we can find the stress on that inclined plane. So for those parts we'll talk about later, but here we just need to know that these 9 components can completely define the static stress at a point. One thing I want to emphasize here that even though we have 9 components, there are not really 9 independent components, because everything in our mechanics material set, everything is in equilibrium. So let's say we have all this force applied, the structure is in equilibrium, and we take a small cube around this cube point, around this point, and since the whole structure is in equilibrium, the small cube we took from the whole structure should also be in equilibrium. So based on the equilibrium of this small cube, we can derive that some of the components should be the same. Let's do a simple derivation. Let's take a plane that is, take the z plane. So we only take this one, and of course on the opposite face we have these two also. So let's say we just consider the shear stress on the x plane and the y plane. It becomes a square. And of course, we have on the x plane in the y direction, on the y plane in x direction. And I didn't draw the stress component on this plane, and back side. This should be the same, right? So let's put it here. Tau x plane y direction, tau y plane x direction. So since it's in equilibrium, we should know that this stress, shear stress, if we only check this plane, and bottom and left side, it should not rotate the small cube. So there should be a moment equilibrium equation. Let's check the moment equilibrium equation. So let's say if it's a moment about z-axis equal to 0. So it should not rotate on this plane. And let's assume that the edge length of the square is a. And the surface it applies on is area. The area is delta A. And since we take from cube, so the area here, area on this surface, area this surface, area this surface should be the same, all delta A. And edge length there A. So the equilibrium equation, what you can write is, of course, this one and this one will generate a counterclockwise rotation. So let's say we have tau xy, and this is a stress. Moment equilibrium is about force and moment arm. So stress convert to force, we times the delta A, the area. This becomes the force. So this becomes the force generated here. Moment arm. So this, if we, so this is a couple. So the distance between them is A. So this is the moment generated by this one and this one. And if we assume the area here is A, the area here is A, and edge length is A, delta A and A. And similarly, tau yx will generate a clockwise moment. And this counterclockwise and clockwise moment should be the same, so that your whole cube will not rotate. So this is a simple derivation. And now from this simple derivation, we know that tau xy equal to tau yx. That's what I said, 9 components in the state strain matrix. They're not 9 independent components, because if you want your structure in equilibrium, and by using the equilibrium equation, moment equilibrium equation, you always have tau yx, tau xy equal tau yx. And similarly, we can have tau x Z equal tau Zx and tau YZ equal to tau ZY. So this means that back to the state stress matrix here, it's a symmetric matrix. So XY always equal to YX, XZ always equal to ZX, YZ always equal to tau ZY, so that your structure will not rotate. So now this 9-component state stress matrix becomes 6 independent components. Where on the diagram is the edge length and area? So this I draw this one like it's simplified. You just go back to here. For here we only check the component this one, and but bottom surface we also have the tau yx, and on the left surface we have the tau xy. So we assume that the area here is delta A. So the shear stress times the A area delta A become the shear force on this area, right? And same thing at the bottom. And the distance in between is this A. So when we have this one, it basically means the moment tau xy delta A times A equal to the moment generated by shear stress tau xy on this surface and on this surface and this distance between them. Make sense or not? It is only for a cube because wouldn't different edge lengths affect them. We want to simplify our derivation to check the state stress at a point. Of course, we naturally think that if we want to know the state stress at a point, we take a small cube. But of course, if you want to take a, let's say, I understand what I mean. Let's say the edge length, they're not the same. You can do the derivation after class. You will get the same answer. You'll get the same answer. Or you can talk to me during office hour. I cannot do the derivation here now because we have the content when you finish it for this 75 minutes. But if you really want to, let's say you have the edge length different, it's not really a cube. You can still do the derivation, shear stress, and area it acts on and distance between them, and have the moment equilibrium equation. You will have the same thing. Why the same thing? Because if you go back to definition of stress is force over area, and then you times area. And yeah, so we can talk about in detail during the office hour, like what if the edge length is not really the same. I can show the derivation to you during the office hour. But for our simple derivation to check the relation between the different components, we naturally consider we take a cube around the point. So now these 9 components in the state stress matrix only have 6 independent stress components. To define the state stress at a point. So sigma x, sigma y, sigma z, and tau xy, tau xz, tau yz. These are the 6 independent stress components. It can completely define the state stress at a point. So now we're done with the whole 1.4 section 1.4 for the theory part. Any question related to this part? So just do a simple test to see if you guys truly understand this part. Let's see if you can tell the subscript of the shear stress generated in the structure. Let's still use the coordinate system, left, right. It's X, upward is Y. And of course, right-hand rule, outer plane becomes Z. So let's separate this one. Let's consider this two structure. It's not like go back up here. Let me rotate. So you can see the whole thing. How about this? So now let's say if this is coordinate system, let's only check this part. For this part, we know that there are shear stress generated at pin A and pin B, and of course, A and B, the symmetry is the same. So what should be the stress component? What is subscript of the tau for pin A and B? It should be the same. Anyone? Based on what we just learned. So what is the subscript of the shear stress generate on the pin here? What you need to tell me what the subscript yx. Thank you. What if we have a structure like this? We still using this coordinate system. We're still using, now we are checking this structure. Let's say this one, they're different structure. Let's ignore this one now. For this structure, we also have the pin A and pin B, and we still have this coordinate system. What is the component? Stress component, the subscript of tau. XZ. GX, yes. The first subscript is always the plane. The second subscript is the direction. So for this one, it basically means that, okay, this is a plane, and the plane of this shear stress generated should be the Z plane, and it point towards X direction. So the subscript should be tau ZX. Z means plane of the stress generated on that Z plane, and X, it means the shear stress pointing toward X direction. Yes. So how about this one? We talked about in the first chapter that there is a shear stress generated on this AA. Yes, thank you. So on this AA plane, this is the Y plane because it's facing the Y direction, and the shear stress, of course, is in the X direction. So it's tau Y X. Tau Y X. Now, last one, we are done. Same coordinate system. I think I can rotate now. It's larger. Let's say we have the pin at D. The pin here. What is the subscript for shear stress on the pin D? ZY. Thank you. It's on the Z plane and in the Y direction, right? So again, for the shear stress on the pin D, the plane is facing the Z direction. And well, if you apply force like this, you would expect the shear force in this way. So it's in the Y direction. So it's tau ZY. The first two. Okay, let's go back. Move organization here. So, do you remember in this problem we have the tensile force in this steel bar? So basically for the pin A and pin B, the shear stress is on this plane and in this direction. And for this plane, it's the y plane because the plane itself is facing the y direction. And the force direction is in the x direction. That's why we have the tau y plane x direction. This is the first one. And as I said, let's assume this is complete two different structure. For the second one, if we have the same coordinate system, now again, the steel bar has tensile force in between, and this tensile force for the payment itself, it becomes the shear force. And shear force, now you can see this is a pin. And this shear force is acting on a plane that is in the z direction. So it the first subscript is z. And again, the shear force direction is in the x direction. X. Make sense? Okay, you're welcome. Any other question? So I added this section from chapter 1 to here because when we learn the shear stress, shear strain, there's always substitute here. I want you guys to know what it really means, like x, y, y, x, z, x, y, z, everything. So now let's move on to chapter 2, the shear strain and shear stress. It's 2.7 shear strain. Shear strain, of course, it represents that if you remember like normal force, normal stress, and normal strain. Strain is the definition, right? The definition of normal strain is the elongation delta of the original length L. The shear strain here, since it's generated by the shear force, there's nothing really like in the normal stress situation, like extension, contraction, or anything. It's really the change of angle. So you just imagine that there's a cube and you have the shear force applied to generate, you have shear stress, and the structure itself will not have elongation or contraction. But what will happen, the deformation itself, it becomes change of angle. So let's say originally this is 90-degree. Now, because the shear force applied, it generates shear stress, it has a stress, it generates deformation. The deformation is this angle changed. There's a reduction angle here. And the reduction angle is defined as the shear strain. It's the deformation generated by shear force. So let's say originally, this is x plane, this is y plane, this is 90-degree. Now after deformation, the original 90-degree becomes half of pi 90-degree minus gamma xy. This gamma xy is the definition of shear strain. Or we can simply say that it's the reduction of angle. That's originally point toward x and y plane is originally 90-degree, and the reduction angle becomes the shear strain. Let's say for gamma xy, and of course the same for xz, yz. The definition is very, very similar. So for gamma xy, it's a reduction of the angle of interior angle. Formed by two faces oriented toward the positive x and y direction. you can consider it's either this angle or this angle. So it's the after shear force applied, it's a reduction of this angle. It's already 90 degree, now it becomes 90 degree minus gamma xy. This gamma xy becomes the shear strain. So a reduction of an interior angle formed by the two faces oriented towards the x and y axis. And of course, if the gamma y z, then becomes positive y and z. If zx, it becomes the z plane and y and x plane. So this is definition of shear strain, and of course the reduction angle, the unit we use radians. Or we can just say that it's dimensionless because if you remember the normal strain is the elongation is length of length, elongation of the original length, so there's no units. Shear strain, radians basically is also considered as no unit. So don't use degree in your calculation, it's radians. And a very simple, too simple situation when you read textbooks, sometimes to say the simple shear and pure shear, sometimes students get confused. So simple shear is basically you have, let's say you have the bottom surface is clamped to a supporting structure and apply a shear force on top. And this is the reduction of angle. This is original 90 degree. Now after shear force applied, it becomes this one. So this angle, reduction angle, becomes the shear strain, and this one is considered as a simple shear. And this one is considered as the pure shear. It's just the name that you probably will frequently see, but it's not really important for calculation. So you can just consider, now let's say it's origin 90 degree, and now after deformation caused by shear force, this one plus this one becomes the reduction of the interior angle. That's origin 90 degree, right? So, or you can consider this is pure shear is simply you have this shear strain generated and then it has a rigid body rotation and becomes pure shear. But of course, it's just two basic concepts. When you read textbook, I don't want to get confused, but it's not really like very important for your calculation. So this is definition of shear strain, simple shear and pure shear. And another thing, as I said, shear stress was a relation between the shear stress and shear strain. If you remember, we talked about that for 1D situation, when you have tension compression, we have the normal stress, we have normal strain. And the relation between these two, what the relation between these two? Normal stress and normal strain. Anyone remember? What the relation between the normal stress and normal strain? Anyone? Young's modulus. Thank you. Normal stress equal to Young's modulus E times normal strain, right? So the relation between the stress strain in normal in the 1D tensor compressive situation is Young's modulus, and there's something similar for shear stress. Shear strain situation is called the shear modulus. Yeah, it should be stress. Strain times Young's modulus. Strain times Young's modulus equal to stress. And here is shear stress equal to shear strain. How to write down? Times shear modulus. G here is the shear modulus. And similar as Young modulus, as I said, is more of a material property. So if you know what material you use, you know what is Young modulus. And similarly, if you know what material you use for the structure, you know what is shear modulus. So you can use this one to find a relation between the shear stress and the shear strain. And of course, this equation is only within the proportional limit. It's before the plastic deformation generated. If everything in our mechanics materials should be within the proportional limit, should be small deformation. we do not do anything when it get into the plastic deformation range within proportional limits. And of course, since it's within the proportional limit, it means that it's very small deformation. And for mathematically, for small deformation, we know that we always have the approximation gamma, this angle equal to tangent gamma. This is very important when we do calculation later, to find a relation of the this dimension and this dimension. So basically, for very small angle, small deformation, everything before proportional limit, this gamma equal to tangent gamma. So you can write gamma equal to tangent gamma equal to this one over this one. I will show you in the example problem. So this is the Hooke's law for shearing stress and strain. And of course, this is about XY. Similarly, we have the shear stress on the y plane in the z direction equal to shear modulus times shear strain y plane z direction. And similarly, z plane x direction shear stress equal to shear modulus times the shear strain z plane x direction. This is it's not V, it's gamma. I don't know how to write. It's the shear strain, the gamma here. Gamma equal to tangent gamma is the small angle approximation. Because everything in our mechanical materials we consider is within the proportional limit. So everything is in the elastic range. This also equivalent to the deformation is very small. This deformation here is exaggerate deformation, but in the real structure, you just imagine that you have a steel or aluminum structure, you have some force applied, the deformation is very small, it's not visible. So for the small deformation, we can always mathematically always have gamma equal to tangent gamma. Top graph here. Okay. Any question for this part? If no, we can start the example problem directly. And rotate. And are you done? Can I move to the example problem? Okay, I can show you our task also because we only have 20 minutes left. So this is the first example problem. The plastic block, which is the gray thing here, is bounded to a rigid support. This you can consider this is glued to the wall. This rigid support and a vertical plate. The plate itself, there's no deformation. You can consider this is also a rigid body. The deformation is really in this plastic block. So of course, when this force is applied like this, it's a shear force for this plastic block, right? And it will generate shear stress and shear strain. Shear modulus is given 150 KSI. Determine the deflection of the plate. So it's basically how much this plate will move downward. how to calculate the deflection of the plate. We know that this plate itself will not have deformation, right? This is a rigid body support. The only thing that will generate deformation is in this plastic block, and of course the shear modular block is given. So let's say for this, we know that there should be deformation generate on this rectangular shape on this area. So now to simplify, let's put it here. Let's assume that this is a rectangle on the side surface of the block. And of course, we have 4.8 inch and 2 inch here. So this one is this surface. And you should expect that when the force P is applied, the deformation, of course, without calculation, you should expect that deformation, exaggerate deformation should something look like this. Let's remove the dimension here. Right. So this is after force applied. And this is original 90°. After deformation, the reduction angle, this will become the reduction angle. So now the shear strain should be here. This is gamma, shear strain. And the question asked about the deflection of the plate. So from this point to this point becomes the deflection of the plate. So this is the question. Let's use delta to represent the deflection of the plate. So this is basically what the question asks, what the delta after the force applied. How to calculate this one? Let's go back in the conceptual part. I said, since it's small deformation, we always have the gamma equal to tangent gamma. This is very important because it can make a connection of the strain and this delta. And since we have a shear modulus, we can have the shear stress. Since we have force, we can calculate shear stress. So now we kind of connect everything we learned so far. We said for small deformation within proportional limit, tangent gamma equal to gamma, and tangent gamma here equal to this one over this dimension, and this dimension is 2 inch. This is 2 inch. So tangent gamma equal to delta, which is deflection plate we want to calculate, over 2. And shear strain, of course, we just learned gamma equal to shear stress over shear modulus. And shear stress, we learned from the previous section, always equal to shear force over area. Right, and we're done. We know the force applied, we know the area that carried the shear force, we can calculate shear stress. With the shear modulus given, we can calculate shear strain. So when the shear strain is given, since small angle deformation, we can always have an approximation gamma equal to tangent gamma equal to delta over 2, and we're done. So let's say stepwise, first step, second step, third step. Let's do it one by one. Shear stress equal to the shear force over area. What is the shear force toward the area in our problem? Shear force 55 kip, right? Let's convert to pound and use inch as our length. What is the area? Anyone? How to calculate? What area should I use here to calculate the shear stress. We have the dimension 3.2, 4.8, 2. 3 dimension. 4.8 times 2. Any other opinion? 3.4, 3.2. Yes, it should be this area. So be very careful. This side surface is used to check the deformation generated by shear force. But this surface, this area is not the area that actually carry the shear force or carry the shear stress. Which area is carry the shear force? Is the contact surface between the plate and the block. So it should be this area. And this area should be 3.2 times 4.8. Be very careful what area you should use to calculate shear stress and what area should we check for the deformation. So the area should be 4.8 times 3.2 because this is the actual area that carry the shear force. PSI. Second step, shear modulus given. So this step is easy. Shear stress over shear modulus. Shear modulus 150. Shear strain radius. It's an angle. It's a reduction angle. It's here. Now, the third step, delta. Since gamma equal to tangent gamma equal to delta over 2, so delta equal to 2 times gamma. So 2 is the dimension here, so it's inch. Inch times the radius, inch, unit is inch. Gamma is a shear strain. Gamma is a shear strain. Shear strain is a reduction. Let's back to the conceptual part we talked about in this section. Gamma is the reduction of interior angle formed by two faces that originally in the positive x. So originally this is 90 degree. After shear force applied, there's a reduction angle. Let's say this angle or this angle. So it's originally 90 degree. After shear force applied, there's a reduction angle. And this reduction angle is a definition of shear strain. Clear? Any other question? Any other question for this example problem? Which drawing? This one? Okay, so this red rectangle represents this side surface I put here, right? It's originally, let's say, this angle is originally perpendicular, it's already 90 degree. Now, because the P applied, you should expect that this is after deformation. This is after deformation, of course, it's actually after deformation. Now, the original 90 degree change to this one, and now this becomes the reduction angle, this gamma here. This is the definition of shear strain. And since it's because a small deformation, gamma equal to tangent gamma equal to delta over 2. Thank you for helping me answer the question. Yes, radians is unitless. Yes. Radians times inch equal to inch. Any other question? Any other question? If no, let's move on to the second example. Hope we can finish before 45. Wait. All right. Yeah, I think it's the correct one. Wait, this is a very similar one. So, so this is a force is applied on this structure, but this structure itself does not have deformation. The deformation is in this gray block. So the maximum allowable shearing stress is 60 psi for this gray block. And displacement, the displacement of the beam should not exceeding this is the allowable displacement. And force applied is this one. So asking about the smallest dimension B and the smallest required thickness A. And of course, the two thresholds to calculate these two dimensions, one is the deformation, one is the allowable shear stress. So first, again, we can, based on the shear stress threshold value, we can have an equation tau equal to shear force of A. And this one should be lower than 60. Shear force here should be equal to 5 P. Equal to P. Area. What area should we use? For calculating shear stress generated by this shear force in the gray block. What area should we use?
A times B.
Thank you. A times B. So this one should be lower than allowable shearing stress, which is 60 psi. So now B should be greater than 10.4 inch. So we calculate one. The second one is the deformation. And again, deformation, let's put it here. We are checking this side surface for deformation because now on this surface there's a reduction of angle that's origin 90 degree. So let's put it this way. Say originally we have for this red surface, we have this rectangle, I put it here. And after deformation, similarly, I put it this way. Right. Let's say for this force applied here. And now this becomes the reduction angle, so this is a shear strength. And the requirement is that this dimension is the threshold value is given. And ask about what the required thickness A. So A is here. And of course, we know that from this figure, we know that the gamma equal to tangent gamma equal to tangent gamma equal to A over A. And the gamma also equal to shear strain equal to shear stress over shear modulus. Since the shear stress should not exceed 60 psi, shear modulus is 130. Yes, 130 psi. So this is our shear strain. Now back here, based on relation between the gamma and A, this equation we can calculate A equal to so dimension of A equal to 0.813 inch. For the question in the chat, displacement, this is given here, given information in the problem statement. So this displacement should not exceed this value. That's how we use to calculate the dimension A. So basically, shear strain gamma equal to tangent gamma. So this edge length over this edge length in this triangle, right? Gamma equal to tangent gamma. And shear strain also equal to shear stress over shear modulus. So this can be calculated. So in these two equations, we can calculate over 2, because this dimension is 2. It's 2 inch here. Because this dimension is 2. And in this triangle, gamma equal to this edge length over this edge length. So that's why we have the delta over 2. That's how we got 2. And similarly, we have the threshold value here. We have the A that we need to calculate here. And the gamma in this triangle equal to tangent gamma equal to this one over this one. Another question?
Sorry, can you go back slightly up to see what G is equal to? Sorry, what is G equal to? 130 KSI or PSI?
The shear modulus. Back to the concept
PSI.
of shear modulus. So it's a similar term as Young's modulus. Young's modulus is for is for normal stress and normal strain. Shear modulus for shear stress is a relation to shear stress and shear strain. Clear? Yes, I use conceptual part because some students probably don't know what the shear modulus means. That's why I go back to conceptual part. I know it's about the example problem. Shear modulus, similar as Young's modulus, is a relation between the stress and strain. It's a material property. Any other question? If no question, we're done for the class today. Thank you for coming and have a great day.
Thank you. Have a good day.
You too. Thank you. Thank you. If you have any question, you can come to my office. I will change the Zoom link to the office hour Zoom link. You're welcome. Thank you. When will exam grade be posted? I told TA to finish grading before Thursday night. You're welcome.